Hello, this is part two, and I think we left off with the electromagnetic spectrum chart, and so we'll continue on from there in part two and get into actually understanding the forces and causes of the seasons on Earth. One of the things we're going to have to discuss is that not all objects radiate all wavelengths of radiation, and some objects radiate different types and more or less degrees of certain types of radiation. We have an example, and just as a background, we're really trying to understand how the Earth and the Sun compare to each other, and almost kind of a almost theoretical concept is a black body is something that absorbs all wavelengths of radiation and then radiates exactly the same amount of energy right back out. And these, are very rare, if impossible, to find in nature, where you find a perfect black body, because the reality is some objects actually absorb certain wavelengths and reflect others, and they don't perfectly then absorb and re-radiate energy at the same wavelength. Often what ends up happening is we'll end up finding is that objects like the Earth absorb sunlight and then re-radiate heat. And so they actually, because the Earth is a different temperature, they actually re-radiate very different energy than they absorb to begin with. And this comes into where we start talking about the Stefan Boltzmann laws that, hotter objects tend to radiate more energy per surface area. So when we're trying to make sense of this idea of energy, the sun being a much warmer surface than the Earth is going to produce, and it's not so much that you have to follow this formula, but one of the rules that Stefan Boltzmann says is that hotter objects radiate more energy per surface area, and it's going to be no shocker that the sun not only produces a different type of energy and radiation, but it also produces more per surface area. Gray bodies are objects that are more realistic, that they tend to emit some percentage of the radiation based on their temperature. They're not like a black body that emits the actual same amount of energy they absorb. They produce the same amount of energy out. The reality is that most objects in the universe are gray bodies, and that they re-radiate some percentage of the possible that they could radiate, because the reality is some of the energy is absorbed, some of it is reflected, some of it is scattered. So for example, if the Earth was a black body radiator from the sun, literally it would radiate every inch of radiation it would absorb. It would radiate every calorie of that same amount of energy right back out to space. And that's not the way the Earth works, and thank goodness it would be, because our planet would be baking. So we'll move on. There are certain rules to understand how to understand the Earth's radiation versus the sun's. And I don't know the correct pronunciation. Wien's law might be the correct pronunciation here. But what he's trying to do is that there are general formulas that once you know the temperature of an object, you can kind of lock in on what type of radiation it typically produces. If you're a fan of science fiction movies and you follow The Predator, and you've seen the movie The Predator, if you'll notice, the Predator can flip through these different lenses and actually see the landscape using different types of radiation. That's kind of an interesting application of this process, is once you understand the temperature of an object, you kind of understand what kind of radiation it produces. Now, it doesn't say on here, but the sun's surface temperature is about I think the number is about 5 to 10,000 degrees Fahrenheit. The surface temperature in terrestrial means the Earth. Terrestrial radiation is the Earth's average temperature is about 59 degrees Fahrenheit. So when we look at the electromagnetic spectrum chart, we can kind of compare that the sun tends to produce shorter wavelengths like visible light and ultraviolet light and gamma radiation, which we've already talked about, that we can see that the sun is primarily producing visible light, And wavelengths from around 5 to 40 micrometer, these are wavelengths of infrared, and this is the Earth's emissions. And you can see that the Earth primarily maxes out its emissions of radiation in wavelengths that we call heat. So what's very interesting is that when you're going outside, the sun is giving the Earth radiation. The Earth absorbs that solar radiation, which is visible light, and converts it into heat. So when you go outside and want a suntan, you're using the sun's visible radiation to do it. But when you actually realize it's the heat coming off the Earth that ultimately powers the temperature and the different temperatures we see with the different seasons on the Earth. So simply put, the Earth and the sun and the Earth are actually, their primary emissions are in different wavelengths. The Earth being an emitter primarily of infrared or heat, and which is long wave, and the sun over here is primarily producing short wave, which is visible radiation. One of the things we have to understand about the seasons is that the sun's shortwave radiation that it is spreading out towards its solar system, that there is a rule called the inverse square law, and there's a very fancy formula here that you would need to understand. And we'll come back to this number here called the solar constant, and we'll come to that 1,367 watts per square meter. But I'll try to explain this in layman's terms here so you can have a sense of it. Is that what this law is basically saying? When the sun is emitting primarily its shortwave radiation out to space, the planets that are closer in are naturally going to get more radiation, because the farther the planet is from the sun emanating the radiation, the more the sun's radiation gets spread over a larger area. So here is Mars's orbit, here is Earth's orbit, and the inverse square law would say because the Earth is much closer to the sun, that the sun's radiation is being spread over a much smaller area, and that's why the Earth is more likely to get a higher level of shortwave radiation from the sun than, let's say, Mars, because Mars is about 40 to 50 million miles further away from the sun than the Earth is. And obviously there are planets inside the Earth that are even closer, like Venus and Mercury, and that's why Venus and Mercury are more likely to get a higher degree of shortwave radiation. So that's the inverse square law. As you look as the planets, as they move around the sun, obviously the planets further away get a weaker dose of the sun's radiation because the radiation is being spread over a greater area with their wider orbit. One of the final themes for the second video here is really looking at the Earth and its specific orbit around the sun. And one of the obvious things you might think, well maybe the Earth and its seasons for places is going to be based upon Earth's proximity. And when we actually look at the Earth's movement around the sun, we call it a revolution. Now, as a kid growing up, I thought that was the backup band for Prince, but that kind of dates me and my age. The term revolution is also used by historians when we talk about times of war. But in science, a revolution is what a year is. It's the whole idea of how the Earth moves around the sun, and it's this revolution that our ancestors have been trying to figure out a year to understand how to set a calendar. And I will show you a picture, but there's two specific periods in early January and early July that we're going to come back to, called the perihelion and aphelion position. And when we look at the Earth's orbit around the sun, it moves kind of in a counterclockwise motion, and the sun does not sit perfectly in the middle. It's actually slightly tilted to one side, so that in January, the perihelion position, the Earth is actually 3 million miles, 91 versus 94 million, so I was right, 3 million. That in January, the Earth gets its closest point to the sun at 91 million miles, and in July, we are 94 million miles away from the sun. So the question is, well, since we're 3 million miles closer to the sun in January during the perihelion position, that should be summer. because we're closer to the sun's shortwave radiation that it's emanating out. And in July, this should be winter because we're 3 million miles further from the sun. We just studied that law that said the further you get away from the sun, like Mars, the energy gets spread over a greater area and it should become cooler. Well, the question becomes to you is, well, you know, in the northern hemisphere, this is the exact opposite of what we would expect. In July, that is typically the warmest month in the northern hemisphere. And in January, this is our coldest month. So I'll end the second video here with asking, how is it possible in July that we're actually in our